We're going to begin with a quick overview of USB PD. We're going to talk about, from a charger perspective, because I'm in the battery charger group at TI, what does that mean for a charger if you have a system that's going to charge off of USB PD? Then we're going to talk about some new products that TI has that, not surprisingly, fit the bill. And then at the end, I'm going to go through something I think is very exciting, a autonomous PD charging chipset. So I'll tell you what that means when we get there. But basically, this is a two-chip set that will autonomously do PD charging without an external microcontroller. We'll tell you more about it when we get there. The PD market is growing really fast. That's what this slide tells you. And it's interesting. I think if you look through about 2018, you'd see very fast growth, but it's in the PC market and it's in the cell phone market. And then somewhere around 2018, you reach this critical mass where people go, you know, everybody has one of these adapters at their home, a USB PD adapter, or a lot of people do. Why don't we use it to charge power tools, to charge drones, to charge all of these other different applications you see here? So as that conversion has happened and USB PD has moved out of just a personal computer space and phone space into all these other applications, there's this second wave of just exponential growth. The question then becomes why? Why is it so popular? A lot of people on the phone, I imagine, are designers, and it's not a good enough answer that you're going to design it into your product just because everybody else is. You want to know why is it popular? Why should you consider it? One thing that is widely touted is the ability to support multiple different voltages from a single adapter. So if you're like me, you've got barrel jack adapters at home, you've got a 5 volt, a 12 volt, a 20 volt for certain, maybe you got a 9 volt, and you can always find every adapter except the voltage you actually need at any given time. So the first thing that USB PD does is it takes all of those different barrel jack adapters and it combines them into one adapter that can supply all of those different voltages. The other reason that I'd say it's really become popular as of late is its ability to supply up to 100 watts. So when USB first came out, USB 1, I think it was maybe 100 or 150 milliamps. It was really just designed to handle like a mouse or a keyboard. And then USB 2 went to 500, USB 3 went to 900. Then when people started charging their phones, they came out with the BC 1.2, battery charging 1.2 spec, and the USB Type-C spec came after that. And these allow you to charge up to 3 amps, which is really, I would say, the practical limitation of 5 volts when you start looking at how much loss you get through a typical cable. Once you go past 3 amps, your cable losses and your drop through the cable becomes such that you might see as much as a volt drop in the cable. So you really can't go much higher than that. And that's a 15-watt limitation. But what USB PD does, as I kind of mentioned before, is it allows you to go up to 20 volts additionally. And that has just opened up the market for all different types of products that people can now consider designing USB PD into their product as their main charging solution and replacing their old barrel jacks, again, up to 100 watts of power into their system. Now, we've talked about flexibility, and not only the flexibility of all these different voltages, but you may know that USB also supports a concept called USB on the go, and PD takes that one step further. So with USB on the go, a host can actually sync power. Normally, the host is always providing power, but with on the go, devices can provide power and the host side can sync it. With USB PD, they take this one step further to where you can actually change power roles after a connection is already set up. You can go back and forth, and there's a very flexible mechanism to do this. So if you take a look at the ability to move power in either direction, and then you combine that with the flexibility of 5 volts through 20 volts, this is fantastic for the end user, but it provides a design challenge for anybody that's putting one of these systems together. Let's say that you have a 4S battery that's going to charge, up to 16.8 volts, we'll say, and you have a 15-volt input coming in. Well, the battery may have discharged down to 13 volts, and you're going to have to begin by doing a buck operation to charge that battery. And then at some point, the battery will get to exactly 15 volts, and you're doing what we call buck boost. And then you even need to boost it up to get through your 16.8 volts. And by the same token, if somebody puts you into a mode where you're supplying power out the USB Type-C port instead of syncing it to charge a battery, you always have to begin with a 5-volt. And then you may want to support up to 20 volts. So you get in the same situation. Whether you're a 2S, 3S, 4S battery, you're almost well, for any of those, you would be bucking down to the 5 volts. But by the time you get to 20 volts, you have to boost. So what you're going to need in order to handle one of these designs is a charger IC, which is capable of doing buck or boost in either direction. And of course, that's what we're here to talk about today. So we have a new series, the 25790 and 25792. We're showing the 25790 on this slide. The 25790 is a ball grid array package, and the 25792 is a QFN. So that's the basic difference between the two packages. But otherwise, they're very similar devices. And there's some really neat features here. We're going to talk about the way the buck boost controller works, but you'll notice here that there's 4 switching FETs, Q1 through Q4, that are shown in the center of the device. And we have 2 of them in front of the inductor and 2 of them behind the inductor. And as you'll see in just a moment, that's how we're able to do buck and boost in both directions. But what I'd like to point out on this slide is these are not external FETs. These are integrated right into the package. So you get a nice cost savings, you get a nice board space savings with that level of integration. Then there's a couple of other very neat features. So if you look in the top left corner here, you can see that we have a dual input power mux. This is really useful in the USB power delivery space because you can have the one input for USB PD and then have the second input for a barrel jack. So a lot of people, they want to have that backwards compatibility to barrel jacks, but, because a lot of the devices are in sort of a transitional state where the last generation probably just worked off of a barrel jack. Now they're adding PD. If you want to have that ability to power from both, you can do it with this front-end mux. Or you might be ready to just jump into USB PD, say, forget the barrel jack, we don't need it anymore. If that's the case, you don't need to populate these 4 external FETs. So these FETs, they allow us to, of course, block one pathway and allow the other pathway through. That's what a multiplexer would do. But if you don't need that because you just have one input, then just don't populate these FETs. The device will work in either mode. So you get the feature if you need it, but you don't pay either board space or price if you don't need the feature. And in the bottom right-hand corner, there's a similar scalability with what we call the ship FET. So some designs need to go into an ultra-low power mode. And what the ship FET allows you to do is it allows you to block current from leaving the battery and going out to the system. Now, of course, you can't run your system off the battery if you're blocking the power, but what you can do is put your product on a shelf for a month and have it not burn very much quiescent current so that your battery lasts until somebody buys it off the shelf and begins using the product. So that's why we call it the ship FET. If that's a feature that you need, the ability to basically shut your whole system down and go into an ultra-low quiescent current, then you can populate this FET. If it's not something you need, you don't populate the FET. So we also have a 16-bit analog to digital converter. That's very handy if you have a microcontroller in your system. As we're going to show you, you don't need a microcontroller. We can build a fully capable charging system with absolutely no external microcontroller, but if you do happen to have a microcontroller in your system, then you can measure all the different voltages, your system voltage, your your input voltages on VN1 or VN2, as well as VBus. You can measure your battery voltage, and you can measure your currents into the same and out of the same nodes. So very handy, as well as the ability to measure the junction temperature of the IC and the temperature of the battery via that TS pin. So some really neat features that are on this device. We talked a little bit about how important the flexibility of doing buck and boost is. So I'll go through this pretty quickly, but I just want to review how our force switching FETs allow us to do this. And I want to talk to you about a very interesting way that we handle buck boost operation, which is really an advantage over a lot of other devices that you might find in the market. So what we're showing here is boost mode. In boost mode, the Q4 and Q3 are switching, but the Q1 is always closed and Q2 is always open, and that makes it look like a standard boost converter. During the blue phase here, where you can see the current going through the inductor and down through Q3, we are increasing the current in the inductor. So you would, during that phase, you would see the inductor current ramping up, and that's storing energy in the inductor. It looks like the energy is all getting dumped to the ground, but trust me, it's not. The energy is getting stored in the inductor. And then during the second phase, the red phase, we are instead going to close the Q4 and open up the Q3 switch. And now the current path goes through the inductor out through sys. And that power that was stored in the inductor is delivered out to sys. And during that time, the inductor current will ramp back down. So this is the standard boost mode operation of a boost converter. And then we can see buck mode operates in a similar principle, but now Q1 and Q2 are switching, and the Q4 is always closed. And during this phase, we will charge the inductor during the red portion where we have the power coming in from the adapter. You'll see the inductor current go up during that red portion where the Q1 is closed, and we're actually delivering power to the system at the same time. And then when the Q1 opens and the Q2 closes, now the current comes out from ground, but the inductor will keep pulling that. That's one of the properties of an inductor, using the energy stored in the inductor, and you'll see the inductor current ramp down as it delivers that power out to the system. Now, in addition to just sort of reviewing the way buck and boost work, hopefully this reminds us all why the four switches are important. And the other thing I'd just like to point out is that this is symmetric. So you can see that in addition to, we're showing everything in the charging direction, but you can do exactly the same operations going in the other direction. So these four switches would operate in a similar fashion in order to do an on-the-go type behavior, where we are instead driving a voltage out the VBus instead of pulling current from VBus. One last thing that I'd like to talk about is our buck boost mode operation. And by the way, the device will seamlessly transition from buck mode, pure buck mode, to buck boost mode to pure boost mode. There are three different modes there. The device will seamlessly transition between those. There's nothing you need to do or program. It's all built in, and you know, even if you have transients, you will go out of one mode into another very rapidly. All of that handled by the device with absolutely no user intervention. Now, there are two common ways of doing buck boost mode. What we're showing here as traditional is what is also sometimes called four switch buck boost mode. And there's two phases where in the first phase, the red phase, we close the Q1 and Q3 switches simultaneously. This is going to charge the inductor. I shouldn't say charge the inductor because we're charging the battery, but it will store energy in the inductor, and you'll see the inductor current go up. And then during the second phase, we open those switches and we close the Q2 and Q4, and now the current is going to be delivered from the inductor out to sys. And the inductor current will ramp down as that energy is delivered from the inductor out to sys. Now, there are some advantages of using this mode. one of which is that it's easier to control. The reason it's easier to control is because the inductor current changes very rapidly. So in both of these modes, your inductor current, you can see it, is ramping up at a high speed and ramping back down at a high speed. And there's really just two phases to it. So both of those make it very easy to control. But what we do in the 25790 and 792 is a little bit more complex, but I'll tell you in a minute why it's better for the end user, which is you, of course. So instead of just doing this four switch switching where there's two phases, we actually have four phases where we're doing a buck switching, which is shown on the left, and a boost switching, and we're interleaving them. And this is, as we're going to show in the next slide, the main advantage to doing this is that it's a good bit more power efficient because we're switching half as often. So in each cycle, when you do four switch switching, all four switches are opening and closing within that cycle. In this mode, we're interleaving the cycles, so there's only two switches switching each cycle. First, the two buck switches, and then the two boost switches. So cutting the number of switches that are turning on and off in half is a very big power savings, and that's the main reason we do it. And that's what we show on this slide here. So if you go into four switch switching, then you're going to see a little bit of a drop in your efficiency when you get to that buck boost range. But with the TI method, you get this nice peak actually right there in the buck boost range because you don't have the extra switching loss. So a very good reason to use this method and a very nice advantage of this device. And then just as a summary, we'll show this slide here. You can see that the transition from left to right. So we start in boost, and you can see that the switch 2 node, which is the Q3 and Q4, is switching. Then we get into a buck boost range that's maybe about 3 or 4 volts wide, where both switch nodes are switching, but they're interleaved, as I said. And then we get into a pure buck mode, where you only see the switch node 1 switching, which is the Q1 and Q2 switches. We also, I've been talking a lot about the integrated switching FETs, but we also have an integrated battery FET. And what the battery FET really allows you to do is separate your system from your battery. And this allows us to do what we call VSysMin. So you can specify a minimum system voltage. Let's say that you have a 2S battery and it charges up to 8.4 volts. You can set a minimum system voltage of 6 volts. And now if your battery happens to get depleted below that 6 volts, you discharge it down to 5.5 volts. When an adapter gets plugged in, the switching converter is going to go ahead and regulate at 6 volts, which is your minimum system voltage. It'll actually regulate slightly above it. And then it's going to run the BAT FET in linear mode. And it operates as an LDO so that you can simultaneously charge the battery even though your system is at a much higher voltage. Because, of course, if you didn't have this BAT FET in an LDO mode and you tried to put 6 volts on a 5.5 volt battery, you'd get a huge current going into the battery, which is not what you want. But the BAT FET operates in LDO mode and allow you to control the current to pre-charge that battery. And then once it hits the VSysMin, the BAT FET will completely close, and now you're running the system and charging the battery all directly off of the switching regulator, which of course is a little bit more efficient than the LDO mode. So we do want to get into that direct switching life as much as possible. The other thing that's important is the BAT FET allows you to completely block current going into the battery once the battery is charged. So if you don't have the BAT FET, you can control the converter so that it is trying to limit the current in the battery to 0 amps. But converters always, they have a feedback loop. They can only operate so fast. And if you have a very fast transient, you would still get small current going into and out of the battery every time you had a transient. But the BAT FET completely blocks that so that when your battery is completely charged, you don't have these small currents constantly going in and out. And the reason you don't want that is because, number one, it'll really affect your battery life. And then number two, you can, in extreme circumstances, actually get to a swollen battery as a result. I mean, basically damaging the battery. We talked about ship mode before, so I won't spend too much time on this because we've only got 30 minutes today. But we have two very low power modes that you can go into. Ship mode, which is 12 microamps, and shutdown mode, which is 600 nanoamps. So extremely low power in that case. If you go into ship mode, you can wake up from I2C as well as an adapter plug-in or a button press. With the shutdown mode, it's just the adapter plug-in or the button press. So a little bit more flexibility with the ship mode. You keep I2C alive. You can go in and out over I2C, but the shutdown mode is nice if you need that absolutely low as possible quiescent current. And I also talked about the dual input MUX. You can do various configurations. I talked about using 4 FETs or 0 FETs, but you can actually also put a system together with 2 FETs where you have dual input and your current path on the second path, the VN2, is driven externally. So we have the flexibility for all 3 of those configurations. Basically scale the MUX to whatever you need. We will automatically transition with the MUX when you plug in and plug out. So if there's nothing attached and you plug into either port 1 or port 2, we'll automatically close those switches and power the system from that port. And if you plug a second in, we won't switch. So it's first come, first serve. But then if you have 2 adapters plugged in and you take out the adapter which is providing the power, we will automatically transition to the second adapter. So at any given time, we're making sure that as long as there's an adapter plugged in, it is being used to power the system from this basically first come, first serve algorithm. We also have JADA protection. So this is basically the ability to scale back our charging if the battery gets very cold or very hot. It's a protection that most battery manufacturers are going to recommend. We have a pretty configurable mechanism for doing that. And with these integrated FETs, we actually have very strong efficiency performance. So here I'm showing it for the 25790. The results are very similar for the 25792. And you can see that when we have an 8-volt battery and a 9-volt bus, and of course the efficiencies are generally best when the battery and the adapter are most closely matched, we're getting well over 95% efficiency for the majority of currents here. So everything from half an amp up to 4 amps. And you can see the different efficiencies here. We also have thermal regulation. So even with that fantastic efficiency, if you start pushing too much power through the chip, you will run into a situation where you can't dissipate all the heat. But we have the ability to regulate at 120 degrees C so that you don't have to worry about damaging the device. And it does depend, you know, if you're going from a 5-volt adapter to a 4S battery, you're not going to be able to push 45 watts. But for a good range, you're able to do 45 watts, and in some cases even higher if you have very close matching between the adapter and the battery. So those are the different features we talked about. I'm not going to summarize them because we've just got about 5 minutes left, and I want to use all of those 5 minutes to tell you about a very exciting chipset solution that we have. So the TPS25750D is a USB PD controller, and then the 25790 and 792 are the charger that I just discussed. And these 2 chips work together completely without an external microcontroller. Now you can still add an external microcontroller, and you can interface to both the 25750D and the 25790 and 92 if you want. You can pull different information off of them, such as the analog to digital controller, or you can do some, you know, more control if you really want to have control over the system. But the PD controller will automatically set everything up to charge whenever there's an adapter attached and you negotiate a sync contract. And by the same token, whenever if you have a power roll swap or if the port attaches as a source, the PD controller will drive the charger so that the charger then goes into OTG mode and does whatever voltages are needed to go back out. So all of your charging and your OTG mode is handled directly by the PD controller, no external microcontroller needed. And we have a reference design that's going to be coming out very soon. So I'm giving you a little bit of advanced information here, but it's going to be out, I think, before the end of the year. And you can see here just a capture from Altium of how small it is. And this is the full design on the reference design. I mean, outside of this, we have some probe points and some connectors, but this is all of the components. And actually, there's very few components on the flip side of the board. Because it's an evaluation module, we wanted to give access to everything. I think you could cut this, maybe not in half, but you could certainly cut it by a third if you were to move some of these components to the back and really focus on the layout. And here we show on the left a screen capture from this board where we're attaching an adapter. You can see the CC lines in purple are where the PD controller is negotiating with a PD controller on the other end. And then the serial clock in blue shows where the PD controller is driving the charger. It's basically programming it with the information it needs to turn on the charging. You can see the B bus first goes to 5 volts and then jumps up to 20 volts, all of that being negotiated by the PD controller. And shortly after, less than a second after attach, the charger comes on and it's going to begin charging. In this case, it's at, I think, 1 or 2 amps. And the charger is happening. This is all without any external microcontroller, just using this board. Not only do you have a single board with these 2 devices and no external microcontroller, but you have a single GUI. The GUI allows you to program, as we see on this page, everything from USB PD. So you can tell it what's the maximum power you want, what are the voltages you support. You can read through these questions. I'm not going to read through every one of them, but these are all configuring the USB PD controller. And then you can configure the battery charger from the same GUI. So first you tell it which battery charger you're using. You tell it what you want to charge the battery voltage to, what is the maximum charging current. And we're actually going to add a couple more configurations to this to where you can specify termination current as well as the pre-charge current. So giving you even more configurability in this GUI. You set it up one time in the GUI, you program it onto a flash on the board, which was included in that layout I showed you. And now you've got a fully functioning system that can source or sync current, charge the battery, or generate voltage out of the port from the battery. This is a little bit more information on the 25750D, so I would encourage you to take a closer look at that. But it is a fully functioning PD controller, and much like the 25790 and 792, it has a high level of integration. All the FETs needed are actually integrated onto the device. So all the FETs used in this design integrated inside of the 25750D. So that's how we get to that really small footprint that I showed you on the previous slide. As we said, we are limited to about 45 watts in most cases with the 25790 and 792. If you want to go higher than that, go all the way up to the 100 watts that USB PD can support, well, guess what? We have a solution based on the 25750S and the 25731. This is also, the 25731 is also buck boost, but it uses external FETs, and because of this, we can, handle up to 100 watts in that device. And so if you need the extra power, we have an option for you there. If you don't need the extra power, I think most people would choose the higher integration of the 25790 and 792. here's a little bit more information on that 25731 buck boost controller. I know we're at 9:30, so I will leave this. You're able to download these slides, and I would encourage you to do that. You can take a little bit closer look at this device for systems that use more than 45 watts. And we show both the 25731 and the 25710 and 713. So I would encourage you to look at all of those devices if you have higher power needs. Here's a little bit more details on that device. And I'm just going to wrap it up with this slide. Don't forget about the protection. So you can get a V-Bus short. We encourage you to use the TPD 6S300A to protect against those types of short circuit on on the Type-C input. And we also have some other interesting devices for you to take a look through, as well as some technical articles and videos that I show here down at the bottom. So again, please download this presentation. You can click directly on these different links and in order to find out more information. That's it for the presentation. I know that Jeff has been answering questions over the chat. I don't know if we have the ability to do this, but I'm happy to stay on and answer questions if that's something we can do via the WebEx, or I don't know. I think
yes,
our
we can keep the webinar or the WebEx open. So if anyone has any last questions, Steve and Jeff can remain on for a few additional minutes and answer those in the chat. But thank you, Steve, for a great presentation, and thank you everybody for joining. Like Steve mentioned, you can download the PDF of the slides and watch this recording by the end of day today. And just a quick reminder, we will not have a webinar next week due to the holiday in the US, but we'll pick back up again December 3rd on a topic for child presence and occupant detection using 6 gigahertz antenna on package radar. So thank you, everybody. And like Steve said, we'll stay on for a few additional minutes if anyone has any questions they want to address in the chat. Have a great day.
Hello, I'm Bertram. I have a quick